Hey, what's up everyone? Welcome back to Structure Free Learning. In this video, we're going to do the moment area method again. And in this problem, we've got this beam that's simply supported, pinned at A, roller at B, has a concentrated load at C, and everything is symbolic. So I have the length AB equal to lowercase a, and length BC equal to lowercase b. And hopefully you won't get confused by all the letters and things. And what we want to do in this problem is find the deflection at point C using the moment area theorems, which I've put over here on the right. Bam! Moment area theorems. Now the first thing we need to do is do some basic statics and draw the shear and moment diagram. And we want the moment diagram so we can generate a curvature diagram. And here in this problem, EI is constant, so the curvature diagram is going to look very much like the moment diagram. And so the first thing we want to do is draw that free body diagram. And then use the equilibrium equations to solve for these reactions. So here I used some of the forces in the horizontal to get AX equal to 0. I took moments about point A to get my reaction at point B or BY. And this is this weird P plus P times B over A. And then I'll take moments about point B to get my vertical reaction AY. Obviously you could also take some of the forces in the vertical. And this tells me that AY is minus P times B over A. The next thing we want to do is draw the shear and moment diagrams. And so what I like to do is draw the beam with just the loads and reactions on it. So here's my shear diagram. Let's start at minus PB over A. Go straight across. Here, then I go up P plus PBA, which takes me to P. And there's my shear diagram. Alright, and now I can draw my moment diagram from my shear diagram. And I'll notice that this area here in green, this area is just a rectangle, and it's minus PBA times A, so that makes this area PB or minus PB, and this area here is equal to PB, which will again just be my change. So that means I go from here, I start from 0 because there's no moment, and then I decrease to minus PB, bam, and then I increase up PB, which takes me back to 0 here. So drawing the shear and moment diagram, not too bad. The value of this right here is just minus PB. And that would be my moment diagram. My curvature diagram, because EI is constant, is just straight up dividing by EI. So M divided by EI, and the shape is going to be the same. Everything is just divided by EI. So that's my curvature diagram. Alright, so that was the easy stuff, that shear and moment diagram and reaction stuff, that was all back in statics. Now comes the real stuff, which is applying the moment area theorem to figure out this deflection under point C. And the next thing that we want to do is try to come up with a qualitative deflected shape. And the reality is this is a little bit harder than it really seems. And so one of the things, especially if you have no clue as to how the deflected shape of this beam is going to look like, you got to start with the moment diagram or the curvature diagram. What we know from the curvature diagram is that here segment capital A to capital B, this location right here is concave down, and so is segment B to C, concave down. And so let me draw my beam. And you have a sense from the concentrated load at point C that point C should actually move down. But let's take that out of the equation right now. Put it out of your mind, right? We just know that this going from point A to point B to point C, the whole beam should be concave down. So with no boundary conditions, with nothing, you would probably just say, oh, it probably looks something like this. But the reality is that the boundary conditions at point A are a pin, and at point B is a roller, which means that I should have no displacement, no vertical displacement at point A and point B. Point C is free to move up and down. And so here point B or point C has a concentrated force P applied to it. So I know point C is going to move down. I know that wherever my beam is, it has to pass through point B here because I have a boundary support. And then point A has to be 0 vertical displacement. If you can imagine it, imagine I'm pushing down right here at the tip of point C to make this go down. So then I start back here, and I know I've got to pass through point B while staying concave down. And I go to point A also remaining concave down. Yes! And that's what my deflected shape looks like. And there's no magic formula to this. It just takes lots of practice and exposure to beams and deflected shapes. Alright, so now that we have this deflected shape, what we really want to find in this problem is this vertical deflection at point C, which I will call delta C here. This vertical deflection. Now I'm going to erase this here. This vertical deflection at point C. This beam is not symmetric. I don't know where there's a zero slope. There's the loading is not symmetric. The boundary conditions are not symmetric. There's no fixed support to tell me where I have zero slope. I do know that I have zero deflection at point A and zero vertical deflection at point B. And so this problem is a little bit more challenging only because we have to use additional geometry relationships plus the moment area theorems to solve for this deflection at point C. And one thing to look at is if I start by looking at the tangent line to point A here, the tangent line. So let me draw this tangent line to point A. Bam. There's my tangent line at A. And what I notice is that here, this point to this point right here, this business would be defined as the distance to point C from the tangent line at A. So using the second moment area theorem, I could calculate this, but that's not what I need, right? I need this delta C, this magnitude of displacement of point C. And so the question is there a way that I could calculate this distance right here, which I will just call that, I'll call that D for now. And because I know that the relationship between TCA delta C and here is that this is that delta C is equal to TCA minus D. And so I could calculate this D by using some small angle approximation. If I look here, I know that this angle, I can call this angle phi. And I know if I knew the length of the beam, which I'll call L, from the length of the beam, I could say that D is equal to the length of the beam times phi. And we know that the length of this beam is little b plus little a plus b times phi. Yes. And so if I can calculate phi, then I can calculate this little d. Then I can put it over here using the second moment area theorem, calculate this vertical distance from point to point C from the tangent line at A, and that'll give me the magnitude of deflection at point C. And so it's all about calculating this phi. In order for me to calculate this phi, I've got to look at maybe another point, or think about similar triangles. You know, similar triangles, such a common tool to use in geometry and engineering, right? This ratio, the similar triangle business. And what I notice is that this deflection right here, I could use this portion and this triangle to calculate this angle phi, because I know that this side is a distance A, and this right here would be the vertical distance to point B from the tangent line at A. Then phi is calculated from phi is equal to TBA divided by the length little a. You know, this is really the hard part of the problem, is figuring all this stuff out, especially with this geometry relationship in similar triangles. But now that you've seen it once, you get the sense that, hey, if I need to, I can look for opportunities of using similar triangles, right? All right, so let's go ahead now and apply the moment area theorems to calculate what we need.